Hello and welcome. My name is Timo von Stegman. I'm a software engineer here at Vortexa, and today's talk is going to be called Where's Your Overhead At? And Other Data Processing Performance Tips. So when it comes to programming languages, kind of the default metric that we talk about is speed. How fast can a given program written in a language execute a task? And when it comes to speed, it's no secret, Python is slow. Seen here benchmarked against a litany of other languages, we see Python performs pretty poorly in terms of computational time and is somewhat middle of the pack when it comes to memory consumption. So does this mean that Python is a poorly designed or poorly built language? Well, no. As it turns out, Python is designed for speed, but it's designed to optimize developer speed. Python uses grammar and syntax and abstractions that are designed to make the language easy to learn, easy to write, easy to read, and just generally easy to use. And really, Python is designed for all the problems that are not, let's say, performance critical. If you have a task where it doesn't really matter whether it takes 2 seconds or 20 milliseconds to run, Python is an excellent option because of its ease of use and the speed at which a developer can iterate on the problem and can make changes to the code, and also the speed at which someone can understand what is going on. But what does this actually look like? Well, let's take a look at some base Python code. Here we see a code snippet taken from the pandas documentation, and what it shows is 2 very simple functions implemented in pure Python code. And what I'd like to draw your attention to is the absence of visual clutter. We see there are no square brackets, there are no type annotations, no semicolons. The code is not requiring you to do any sort of memory handling, no pointers, no dereferencing. And when we look at stuff like how a for loop is implemented, we see that this is probably as close to pseudocode as you're going to get in a real language. But it's no secret that if we were to apply these functions to a large set of data, that the performance would be pretty sluggish. So what does the other end of the spectrum look like in the Python world? Well, taken from the same documentation, here we see a snippet of Cython code. So Cython is sort of a sub-dialect of Python, and it's a way of pushing a lot of the operations in your Python code down into the underlying C and C++ layers. And this is really done to get a marked performance improvement. What we see here is we have the same 2 functions, f and integrate f, defined in Cython syntax. And we have a third function down here called apply integrate f, which is there to optimize how our functions can be applied to a large array of data. Now, this code performs really well, not just compared to the base Python code, but it can really hold its own against other languages as well. But what we see in these 2 code snippets is really a very fundamental trade-off when it comes to programming languages and software in general, which is the question of, are you placing the overhead on the developer or on the machine? In the pure Python code on the left, a lot of the overhead, a lot of the thinking has been pushed down on the machine. We said there's no sort of memory dealings, there's no typecasting, all this kind of stuff. So it makes the code very clean and simple for a developer to read and write. But what it means is the overhead and the onus is now on the interpreter to figure out what are the types of my variables. The operations I've been asked to do, can I do them on these types of variables? How much memory do I need to allocate? So all this thinking has been pushed down into the machine. That's part of the reason that why this becomes quite slow, is the machine has to do a lot more thinking for us. In the Cython code snippet, on the other hand, we see that we use like type annotations, we do a lot of assert statements, we use some sort of underlying C structures or C Python structures, and generally it's a lot more verbose. So now, as a developer, we've had to do a lot more thinking, and as someone reading this code, we have to think a lot more about what's going on here and why this code is working a certain way. But what it means is that the interpreter and the computer are now having to do less work in order to execute these functions. And that's part of the reason why this code is far more performant. But if we have this problem that our basic code, while neat, is very slow, and the likes of our Cython code, whilst fast, is a bit of a mangling of different languages and maybe a bit more difficult to interpret, where does this leave us in terms of using Python? Is it time to pack our bags? Should we maybe write our code in a new language? Languages the likes of Go, C++, Java, Kotlin, Scala, Rust, all these languages. If we were to write the functions that we implemented in our previous slide in any of these languages, they'd arguably be easier to read than the Python code and almost definitely be more performant than our Python code. So we're already getting kind of a sweeter trade-off here. Likewise, if our performance bottlenecks are incurred when we apply our functions to a large set of data, well, what if we throw more machines at the problem? We can use the likes of Dask or Spark as distributed computing frameworks to use more nodes and more computers to do our operations. Well, these are absolutely valid and usable options if you're starting a project from scratch. But what about cases, as here in Vortexa, where a lot of our production code is already living in the Python world? Should we take this code and port it to a new framework or move it into a new language? Well, there's a chap who argues quite strongly that we should not do this. And that man is Joel Spolsky. For those of you who don't know who Joel is the co-founder and was the longtime CEO of Stack Overflow. And in his most read blog post of all time, he argues that the single worst strategic mistake that any software company can make is that they decide to rewrite their code from scratch. And there are really two key arguments that Joel touches upon here. He uses examples from companies like Netscape and Microsoft who have decided to rewrite entire code bases or attempt to rewrite entire code bases from scratch, and the huge issues that has occurred for them. And one of the key arguments that Joel makes is that when you optimize for speed, 1% of the work gets you 99% of the bang. And what this means is we see this in a lot of cases where in a large code base, performance bottlenecks tend to be sat within a very small fraction of the code. So if to alleviate these bottlenecks, you decide to move your entire code base into a new language, what you're having to do is you're having to understand what the other 90+% of your code are doing that work absolutely fine. And you then have to translate that into a new language. You have to potentially translate it into a new framework because libraries change and implementation details change. And then you have the actual time penalty of actually writing that code as well. The other problem is, and arguably the bigger problem is, code that's been around for a long time, especially code that's lived in production for a long time, contains a lot of latent information. This is usually in the form of bug fixes. And what this means is that even if you think you're clear on what that code is meant to be doing, it's not always clear to see why it is doing it in a certain way. You may see weird patterns or weird syntax that's used or weird libraries are used and make you think, well, this is probably just badly written code. But what they really are often bug fixes and hacks or workarounds to deal with idiosyncrasies in your data or idiosyncrasies in your infrastructure or your platform. And if the people who have done these fixes for you in the past are not part of the project and not part of the moving of the code, what you essentially run the risk of is rehashing a lot of these old bugs and a lot of these old issues again. And that can turn into a really serious time sink. So essentially what Joel argues is that methodical incremental refactoring is almost always preferable to starting from scratch. So how has this come up, or how we come across this in the scope of Vortexa? Well, one specific example is our vessel events project. Vessel events is a really important core part of our processing. And a few months ago, this was handed over from our predictions and market modeling team to our signal processing and enrichment team. And one of the first tasks was for the new team to get more familiar with this code base. One of the things we started seeing was very old snippets of code that maybe looked a little bit like this. So we could see, obviously, it's doing some operations on a data frame, and it's using NumPy operations here, but it wasn't immediately clear what these to IDX and from IDX operations were actually doing. And after a bit of research and looking into it, it turns out that for those of you who are maybe more familiar with pandas, a simplified example of this NumPy code could be expressed as this. Fundamentally, all it's doing is saying, for every row in this column, tell me if the next value, which we obtained by using a shift operation, is equal or not equal. And we can see already in the case of this pandas version, shift is already maybe a little bit easy to understand, and B, if you have a decent interpreter a decent IDE or any kind of internet connection, you can very quickly look up what this shift method does and work out what this IDX assignment is actually doing. Whereas that's not fundamentally clear from this sort of customized NumPy slicing syntax. Now, should we then go and replace all of these NumPy calls with pandas shift operations? Well, yeah, maybe we should, but there is a catch. It turns out that this NumPy slicing syntax is actually faster than using a shift operation. Now, granted, shifts are not going to be the performance bottleneck in this code, and they aren't. But this is an illustrative example where we have two ways of doing this using two of our really core libraries in Python, namely NumPy and pandas. And there's a real trade-off akin to our overhead trade-off of legibility versus speed. So what we want to look at today is some of the tips and tricks we can use to get performant and neat code when we're doing data processing in Python. And really what we're going to focus on is how we can use NumPy and pandas to do so. So before we move on to the actual performance tips, let's just remind ourselves about what NumPy and pandas fundamentally are. So NumPy here on the left it's been around for a while, and it's really the default numerical programming library in the Python world. NumPy is really fast and efficient at doing numerical operations, and the way it does that is two really core design features. First, a lot of the NumPy operations that come out of the box are actually executed in precompiled C code under the hood, not in pure Python. And what this means is that the operations are just natively faster than pure Python code. The other really important design feature of NumPy is that standalone, it is very much an array programming language, much like the likes of MATLAB, Octave, and R. And the way it does this is it forces you to think about your operations in terms of vectors. The core data structure in NumPy, the NumPy array, is a data structure that is stored in densely packed contiguous blocks of memory, which means access to them is very fast. And the operations you do on these arrays tend to be natively vectorized, meaning it takes advantage of stuff like the SIMD architecture in a modern CPU to natively vectorize operations and thereby significantly reduce the overhead of what your computer has to do in order to calculate what you might want to calculate. Pandas, on the other hand, has kind of developed into the de facto data processing library in the Python world. And pandas is actually built on top of NumPy. So NumPy arrays and NumPy operations really form the core engine of the pandas library. But on top of NumPy, the pandas developers have built a really rich ecosystem, rife with user-friendly abstractions and APIs, and provide lots of really powerful, simple commands that allow developers to do a huge variety of operations to their data sets in a very simple and clean way. Much like NumPy, one of pandas' advantages is also its sort of data structures, and that is the pandas data frame is really a fantastic way of representing and thinking about real-world data. It offers you a tabular representation of your information using columns and rows to represent features and observations respectively. And this sort of two-dimensional data structures can be achieved in other languages as well, but these often tend to boil down to somewhat messy, clunky, nested lists of lists, whereas a pandas data frame really is a far more intuitive and powerful data structure when it comes particularly to working with real-world data. But as is always the case, both of these libraries, for all their benefits, have their drawbacks. So in NumPy's case, NumPy as a library is fundamentally more constrained. A NumPy array, for instance, requires homogeneous data types. You cannot mix numerical data types with string data types, for instance, or even within the numerical world, you cannot mix floats with integers. So what this means is there's more overhead and more thinking on the part of the developer to have to write a bit more boilerplate, a bit more pre-processing code in order to get your data into a structure and into a shape where you can take advantage of NumPy's really fast operations. Pandas, on the other hand, has the downside that its rich abstractions, while making it very user-friendly, make it slower. These abstractions are fundamentally layers and layers of extra functions, extra method calls, which happen under the hood, away from the eyes of the developer, and which just mean that for every operation you're doing, the interpreter and your computer having to execute more operations and do more thinking for you. Pandas, as a library, also shares an attribute with Python as a language that is a very sharp double-edged sword, namely that the abstractions and the ease of use make it very easy to write code that works exactly as you intend it to. It will pass any unit test, any integration test, but do so badly, particularly in terms of computational performance and memory performance. So how can we marry these two libraries together? How can we use their core strengths and try and avoid some of their underlying issues? So the first set of tips I'm going to talk about, I've actually taken or borrowed from this article and the accompanying talks by Sophia Heisler. And she's done a brilliant job of illustrating some of the really key performance tips that we can use when it comes to using pandas specifically. So just as a note, any of the following examples where we talk about this Haversine function, they're all taken from this blog post. So all credit is due to the author here. And fundamentally, what we've got here is we start off with a Haversine function. So Haversine is just a trigonometric function that allows us to calculate the distance between any 2 points on a sphere. And if these points are defined by lat long coordinates, and if the dimensions of the sphere are made equal to the dimensions of the Earth, well, then we can see that we can calculate the distance between any 2 points on the Earth. And all I really want you to focus on here is that fundamentally, this is just a trigonometric function. It's not really doing any sort of magic under the hood. It's just a series of sine and cosine and arcsine calculations. So now let's say you're given this Haversine function, you're given a data frame of values, and you're asked to start calculating some distances. Well, if you're new to pandas, or even if you're new to the Python world, the fundamental way that you're going to think about this is probably going to be the for loop. So in a for loop, we see a very standardized structure. Namely, firstly, we instantiate a list, an empty list, to hold our results. Then we instantiate a for loop. And what we do here is we create an incremental integer counter object I using our range function. And within that loop, what we say is for every incrementing value of I, use this iloc accessor object to get to the ith row in our data frame. Within that row, access the latitude and the longitude values and pass it into our Haversine function. In all of these examples, we're actually calculating the distance between a fixed starting point and a variable endpoint. And then we assign the output of that value, append it to our empty list. And once our loop is complete, we have a list of the same length as our data frame with our respective distances. So how does this cope in terms of performance? So this takes 645 milliseconds to run. Now, this may not seem too bad. It's just over half a second. But there's two catches here. Number one is the data frame Sophia Heisler used in this example has only got about 1,600 records in it. And that's really not that many records. The second problem is, as we just spoke about, the Haversine function really is fundamentally just doing mathematics. And computers are built to really thrive on doing mathematical operations quickly. So it kind of dawns on us quite quickly that 645 milliseconds is probably not fast enough. And to anyone who's used pandas to any extent, you'll probably know that this is not really how you should be doing it. So what are some ways we can do to do this faster? Well, how about one commonly used method, iterrows? So with the iterrows approach, we are fundamentally still looping over a data frame. Iterrows is a built-in method into pandas, so every data frame has this has this method in it. And whilst we're still fundamentally looping, our loop is now slightly different in that we're not using an integer index counter to access our rows. Iterrows actually returns the row object, thinking of it as a dictionary of values for every row. So that means within every loop of this row, we can very simply access the latitude and longitude values, or the keys of that row, pass the values into our Haversine function, and append them again to our resultant list. And then here what we see is that resultant list has been assigned to a new column in our data frame. So how does this actually work in terms of performance? So this takes about 166 milliseconds. So this is about 4.5 times faster than our basic Python loop. So that's already a pretty decent performance improvement. But iterrows is one of those things that is a bit of a catch, especially for novice pandas users, because it's built in and because it looks like the right way to iterate over rows. It tends to be what a lot of intermediate or beginner users default to. But as most of you who have used pandas more frequently will probably know, iterrows is not really the right approach for doing this kind of stuff. Instead, And what most intermediate users will default to and what most users will use is the apply. So apply, as the name suggests, it's another built-in method in pandas. And what it fundamentally does is it applies a function to every row or every column in your data frame. So what we see here is, and apologies for the cut-off code snippet, we see into our apply statement, we pass a lambda function, so an anonymous function, and all this allows us is to get access to a variable. In this case, we've called it row. And then for every row, we access the latitude and longitude. And then all that's missing at the end here is a keyword argument access equals 1. And all that does is it tells our apply statement to go row by row as opposed to column by column. The other thing that we can immediately see is that we've now got fewer lines of code here. We're not having to create an empty list. We're not having to instantiate a loop. Apply does all of this for us. And so how does this now perform? Well, 90 milliseconds. So again, it's about 2 times faster than iterrows. So that's already great. But there is an important caveat here, or an important catch, which is there seems to be a misconception that, well, with a lot of people, that apply is a vectorized operation, which is why it's faster than iterrows. That's actually not true. Unfortunately, Sophia Heisler has illustrated that for us very clearly by using a line profiling tool. So calling a line profiler on our Haversine in our apply call, we see here that every line within our data frame has actually been called 1,631 times. What that means is it's been called once for every row in our data frame. So fundamentally, apply is still looping. This is not a vectorized operation. So can we vectorize this? Well, it turns out we can. But before we show the vectorization, there's one really important catch or caveat that we need to talk about, namely this Haversine function that we see here on the right, which is the exact same as the code snippet that I showed you in the first slide, is already using NumPy to do its operation. So it's already using NumPy's degree to radian conversions, NumPy's cosine, sine, and arcsine operations. And the reason this is important is if our Haversine function was originally built using, say, base Python and using maybe the math library to do these operations, then it would not inherently be vector friendly. So in order to achieve vectorization, we would first need to make sure that we've written our function in such a way that actually allows us to vectorize. Fortunately, this is already the case, so we can move on quite swiftly, but it's just an important note to be aware of that that vectorization is not just a way of, applying a function to a set of data, it's also a concept of how your functions are fundamentally defined. So what does vectorization look like in this case? Well, it's as simple as passing our columns directly as arguments into our function. Under the hood, NumPy knows that even if our 2 lesser arguments are columns or arrays, and our 2 former arguments are scalars, it can deal with all that. That's not a problem. The other thing is, we now have none of the clutter of calling df apply and lambdas. We're simply calling a Haversine function with 4 arguments. So already it's visually much cleaner. But I guess the key question is, what does this look like in terms of performance? And again, we see a marked improvement, namely we're down to 1.6 milliseconds. So that's almost 90 times faster than our apply statement. And again, to illustrate that this actually now is truly a vectorized operation, we can call our line profiler again. And we see that now every line in our function has been called once. So our CPU has fundamentally said, give me this function once, I will take care of applying the operations to a large set of data for you. And that has reduced a significant amount of the operations going on under the hood. And that's part of the reason why this is so much faster. So we're now down from 600 milliseconds in the basic Python loop to about 1.5 milliseconds in the vectorized implementation. But it turns out we can actually do a little bit more. We can very simply do the same thing as before, but call dot values on our columns. Now, what's the significance of this? Well, as you can kind of see in the comment that Sophia Heisler has provided, what this does is it actually calls the underlying NumPy arrays. Now, remember that I said that pandas is fundamentally built on top of NumPy. Pandas, when you call a column from pandas using the square bracket syntax, what you get back is a series object. But when you call dot values on a series object, you get back an underlying NumPy array. And a NumPy array is fundamentally faster and more efficient than pandas series. And the reason we can do this in this case is that we know latitude and longitude are columns containing one homogeneous data type, namely a float representing a degree. And when we call dot values, we see that now we're suddenly taking, instead of 1 millisecond, 370 microseconds. So again, we're almost 3 times faster. So all in all, we've got close to a 200 times performance improvement over a basic Python loop. Now, again, we need to be careful here because we know we can use values in this case because latitude and longitude are homogeneous columns. But to illustrate what's actually going on here, I'm going to borrow 2 slides from a fantastic talk by Ian Oswald, where he shows us what's actually going on. So here what we see is, I believe it's a sum method called on a pandas series. And what we see here is an execution graph of all the files and functions that are hit once this call is made. And we can see under the hood, pandas is calling 25 files and 83 functions in its source code. And although it's not clear here, very few of these functions are actually our efficient NumPy calls. Whereas if we use .values.sum, we see that this execution graph whittles down to 18 files and 51 functions. It's still quite a few, but it's significantly fewer than for a pandas series. And that's part of the reason why using .values is a lot faster. So naturally, you might ask yourselves, well, should we just be using .values everywhere? Again, I have to stress that no. And the reason for this is because, as we said, in the case of that latitude longitude example, we have homogeneous data types, so we know that that conforms to the requirements of a NumPy array. But a pandas series is very powerful. A pandas column can contain any combination of different types and objects. You can have dates mixed with strings, mixed with numbers, and you can't turn that into a NumPy array under the hood, so it doesn't even work in some of these cases. The other issue is a pandas series contains an index as well. Now, an index is very powerful because an index makes sure that your values are essentially alignable to a data frame with the same index, which means that if you're doing any operations that maybe risk shuffling the order of your data at any point, if you're using a pandas series, that's absolutely fine because you can still combine that data back onto your data frame at a later stage because the indexes can be used to align the values. Whereas if you're using a NumPy array and your values get shuffled, well, it's going to be incredibly difficult to realign them, and realistically, you're probably going to end up losing that ordering. So it's just something to be wary of here, that values, using .values and calling the underlying NumPy arrays is a very powerful approach, but it does come with its catches. So those are some awesome performance examples from the talk by Sophia Heisler. But when I saw this talk and when I saw the blog post and similar blog posts, I thought this is great. We can take this away and really start to improve some of our processing. But one of the things is the team I'm in here at Vortex, the signal processing team, a lot of our pandas code doesn't actually do all that much sort of purely numerical processing. We deal with a lot of real world data. So some of these tips weren't really all that valid for our use case, at least not as they're shown here. So what can we do if we think a bit more about some other pandas common use cases using real world data? So to illustrate this example, I've taken some of our Vortexa cargo movements data, and we see here we've got about 900,000 records spread across 15 columns. And we see here we've got mixes of timestamps, integers, strings, and this is really representative of real world data. So what are some of the common operations we might do on this? One of the first ones is conditional statements. Now, this is a bit of a gibberish function, but it's a good illustrative example. Let's say we have a list of countries, Norway, Sweden, Finland, and Denmark, which we call Nordics. And let's say for any given country, we want to find out, is it a Nordic country, yes or no? So we could simply say, if the country is in the Nordics, return Nordic export, otherwise return other export. And, even sort of intermediate users of pandas who are familiar with this concept of vectorization, you see it frequently when it comes to stuff like conditionals or more custom functions, they tend to fall back to apply, which is okay. But let's see what happens if we call apply in this case. So we call apply on the data frame using a lambda to access our loading country column, and this takes 16 seconds to run. Now that's quite slow. Granted, we can't compare this like for like with the applies we saw in the Haversine example because our data set is much, much larger. And again, we're using conditional statements here, not doing mathematical processing. But still, 16 seconds is quite slow. But there is another really important point to make here, which is we've called our apply on our entire data set and used the lambda to access just one column or one attribute of every row. What we can actually do in this case is call our apply directly on that column. And that already gives us a huge performance improvement. We've gone from 16 seconds down to 145 milliseconds. So this is a really important point to make. Just bear in mind, if you are using apply, not all applies are created equal, and you can incur significant performance benefits if you use it correctly. But as we know, apply is still fundamentally a looping approach. So can we vectorize this? Well, it turns out we can. And we can do so by taking a page out of the book of performance databases. What performance databases often do when they're met with conditional logic is instead of branching their code and branching their data to match the branches of our logical statement, they'll actually evaluate both sides of our logical condition on all of the data and then combine those together to give us a correct output. And to do this in pandas, what we can do is something like this. We again have our list of Nordic countries, and we can now make use of a really powerful concept in pandas called a mask. Now, what a mask does is essentially you pass a Boolean statement, so a conditional statement. So in this case, we look at is our loading country inside our Nordics list. So using this very handy is-in method, which just checks that for every record in that column, is it in the Nordics? And it will return us a series of the same length as our loading country column with the resultant rows being true or false, depending on whether they're in the Nordics or not. We can then use a nice trick here, which is to set our new column Nordic status to our default value, which is other export, and then use our mask in conjunction with this lock operation to assign Nordic export. And what this is essentially saying is, give me all the rows where my condition is true, and for those rows, assign the Nordic status value to be Nordic export. And what this results in terms of performance is gone down now to 30 milliseconds. So even compared to our series apply, that's about a 5 times performance improvement. Another way we can do this is by using NumPy and using NumPy's built-in .where method. And you can think of this like a ternary operator in other languages. We have our Boolean condition, which is the exact same as our mask in the pandas example, then our case if true and our case if false. And what we see here is this takes pretty much the same amount of time or a similar order of magnitude to run. And I've just shown this as an illustrative example that there is, even within the vectorization, there's different ways of doing this. I have no personal preference on this myself, so it really is sort of down to you as a developer to choose which one you think is more intuitive or more suited for your use case. But this is a pretty simple conditional statement. What happens if we're faced with something like this? Now, again, this is a complete gibberish function, but what we're trying to do here is to say, firstly, let's look at the time delta between our unloading timestamp and our loading timestamp. And if that is less than 7 days, we call it a short journey. If it's 7 days or longer and the cargo is clean, label it an important clean journey. Otherwise, look whether the loading country is in any of our predefined region lists and assign the region label accordingly. And finally, if none of these conditions are met, just return ignore for that row. And in this case, we cannot use a series apply because we know that we need multiple values from every row. So unloading, loading, cargo, loaded country, etc. So we have to call our apply on our whole data frame. And this takes a minute and 13 seconds to run, which I suppose in developer terms is bordering on a lifetime. So again, as you might have guessed, can we default to vectorization? Yes, we can. And really, we can use the same principles that we use for a simple conditional statement. Namely, firstly, we create masks. So here we create one mask for each of our conditional statements. These are just going to result in mutually exclusive Boolean series. And in order to then get the right result, what we need to do is flip that logic on its head, essentially. And this is, to me, just a bit of a catch in this approach. because now when we think about if-else statements, we tend to think top down, right? We tend to think, here's our first condition, then our next condition, our next condition, and we break once that condition is met. We don't evaluate the rest of the conditions. But when we're using this vectorized approach, we actually need to flip that if-else block on its head and start with our else condition. So much like the previous example, we start with our default value, ignore, and then we need to apply our region masks. Now, in this example, I know that our region lists here are non-overlapping, so it doesn't matter which order we apply them in, as long as they're applied after our ignore statement and before we use our clean and our date masks. And then we, again, obviously go with our clean and our date masks. And we can see that this is really powerful in terms of performance. We're down to 165 milliseconds versus over a minute. And again, as I said, the only downside to me personally is having to flip this if-else logic on its head may not be, or may not seem like a significant penalty when you're writing this, but when someone has to revisit this logic later on, or they might have to sort of change something within that if-else logic or add an extra condition, they can just add that little bit more time to them to understand that this logic is flipped on its head and how this actually evaluates in terms of a simple logical statement. But can we mitigate this sort of small drawback of using the pandas masks approach? Well, we can use numpy.where again. So here we see an implementation using numpy.where. Now, in terms of performance, this is a similar ballpark figure, 200 milliseconds. But as you can pretty clearly see, in terms of syntax and legibility, this is a nightmare. And for anyone who's ever incurred these sort of nested where statements in a code review, you'll know that this is really not a very pleasant thing to have to work with. But luckily for us, NumPy actually provides another really useful tool, which is the select statement. So for a select statement, it's very simple. Much like with the pandas mask, you provide us with the pandas vectorized approach, you apply your Boolean conditionals, which are defined the exact same way as our pandas masks. So we define a list of these conditions. Then for each of these conditions, we define a corresponding result and store it in a results list. Now, the important thing here is the results and conditions lists must be of the same length, and the values in the results list have to correspond to their statement in the conditions list in terms of where they are within that list. Then we simply pass the conditions and the results into a NumPy select statement, and we set our default value, which is essentially our else statement. And we see that this runs, again, similar ballpark, marginally faster than our pandas version, but with the added benefit that our conditions are expressed and evaluated in this sort of top-down manner. So again, this just adds that slight margin of, in my opinion, interpretability for any developer who comes to edit this code later on. So all we see here is, I think both the pandas approach and the NumPy select approach are valid. It really is sort of down to you. I would say agree with your team on a default way of doing this and stick with that. In this case, with multiple conditionals, I would strongly advise to not use nested NumPy where statements. So what we've seen here is in the case of conditionals and how we can use vectorization to gain significant performance improvements there. What about some other cases? What about a data type that is dreaded in a lot of languages, which is dates? So here what we see is, again, quite a simple function. All we want to do is we want to find a delta between our unloading timestamp and our loading timestamp. This returns us a date time object, and then we use the .days accessor to get the days unit for that time delta divided by 7, and that tells us how many weeks it took to do this operation. And again, we can see we need multiple values from each row, so we cannot use a series apply, so we have to apply in our data frame, and this takes about 42 milliseconds. Sorry, 42 seconds, even worse. And you might think now, well, okay, how do we vectorize this? Well, the first thing is you might look at the syntax and think, well, actually, if we replace row with df here, I know I can subtract two columns from one another. I can't just then use .days divided by 7 on that. Well, it turns out almost not quite. If you call .days on a column of date time objects, you'll get an error. But luckily, what the pandas developers have done is thought about this and said, well, if we have a column of date time objects, how can we essentially vectorize our datetime object accessors and methods on that whole column of values. And very simply, it's using the .dt accessor object. So what we see here is we again have our delta calculation or subtraction, and then on that resultant column we call .dt.days, and we can then divide that by 7. And now we suddenly see that this has gone from 42 seconds to run to taking just 25 seconds to run. Now, this is already an awesome performance improvement, but it turns out we can actually do a little bit more, and we can use a tip taken from another talk that I've linked at the end of these slides. And what we do here is we know, firstly, we can take advantage of two things. Firstly, which is we know that unloading and loading timestamp columns are all date times, so it's homogeneous. So we can actually call the underlying NumPy array using .values. The second thing we can do is, instead of having this operation where we're dividing what is still fundamentally sort of a datetime object by an integer value, we can use typecasting to convert our column to time delta object and divide it by another time delta object. So again, it's just taking that little bit of thinking overhead away from the interpreter, and we see this give us about a factor of 2 in terms of performance improvement. But now, obviously, as you can see, the downside is this is a bit more verbose and maybe slightly less legible. But it's just a nice tip to bear in mind if you're doing a lot of datetime processing. So the final tip I want to talk about is coming back to the first example I spoke about with this sort of shift operation. What about cases where out-of-the-box methods are not fast enough or don't exist? So I know we said that shift is not going to be a performance bottleneck, but let's assume it was. Let's assume that our custom NumPy implementation is performant and fast, and moving it to shift whilst cleaner and neater would take us over the edge in terms of our performance time. Well, we can still use our custom NumPy implementation, but what we need to bear in mind is this mantra that I'm sure pretty much every developer has heard in some way, shape, or form, which is that code is going to be read more times than it's going to be written. So what we can do here is we can actually replace our custom NumPy implementation with something like this. So again, you see we've defined our values array, and then all I've done here is, instead of having an inline NumPy where with a condition inside it, I've just moved the condition outside for legibility in this case. And instead of using this array integer slicing syntax, I've now said, tell me where VesID is not equal to the array shift of VesID. But what is array shift? Well, quite simply, array shift is just a custom function that we've built. And array shift, or in any case, wrapping up our custom functionality into a function like this, offers, I'd say, 3 main benefits. Number one is we can give it a descriptive name. Array shift already gives you kind of an inclination as to what's going on here. The second thing is, once we've wrapped it into a function, we can give that function a very extensive and descriptive docstring. So we can tell the user that this is a custom function which emulates the pandas shift functionality. We can tell them what parameters are passed, what the return type is, and we can even give examples of what this might look like in a simple use case. So already the developer has to do way less work to understand what's going on here. The final benefit is, once we've wrapped this into a function and we use the function throughout our code base instead of the custom slicing syntax, we can have that function tested, and we can ensure that it works as intended. And if we make any changes to that function, we can ensure that the changes are tested, and we can ensure that it works the same way throughout, instead of maybe forgetting, if we want to update this syntax slightly and we forget to do it in one place versus others, we can get errors creeping in there. But if you wrap it into a function, that will not happen. So it's just one of those things to bear in mind. It is an edge case. NumPy and pandas are very extensive in what they provide, and they provide ways of efficiently doing things out of the box for most use cases. But if you do come to those edge cases where maybe, let's say, pandas is too slow and NumPy doesn't have what you're looking for, or something along those lines, you can still create custom functions to do what you want, or custom functionality. But as we suggested, just wrap those into functions and make life easier for yourself and anyone else who's going to be working on this code base. So that was the last performance tip I wanted to talk about. A couple of things just to mention in terms of what's not been covered today. So one is .str methods. So for those of you who are more advanced pandas users, you'll know that much like the .dt accessor type for dates, the Pandas API also provides .str accessor for columns of string types. So this allows you to do a lot of sort of base string object operations on a whole column of strings. The reason I haven't spoken about this today is because both when looking into this stuff and when doing it myself, I found that .str doesn't actually always give you a performance improvement compared to sometimes just applying a basic string operation on a column. And it's just one of those things, you're going to be doing a lot of string processing in Pandas. All I would say at this stage is, just spend a little bit of time making sure that you are using the right approach. You might have to test a little bit and tweak and fiddle, but just find what's right for your use case. But in my experience at least, .str isn't as sort of easy a default go-to for performance improvements as some of these other tips have been. The second thing we haven't covered today is the library numxpr, or numerical expressions. This is essentially a library that allows you to define operations and numerical operations as a string and pass them to this library, which then fundamentally compiles those operations down to opcode, making them very, very fast. The reason I haven't really spoken about this is, number one, I haven't used or even personally seen it used in all that many production code bases. I'm not very familiar with it. I also don't find it all that intuitive to use myself. And that might just boil down to a lack of time working with it. So it's just one of those things to note. numxpr is definitely an option, and it's exposed in the Pandas API as well by the .eval method. You can definitely look into this if you really need to etch out some more performance. I just haven't really decided to cover it today, probably more because of a lack of familiarity with it. The third thing I haven't covered today, but that is also important to mention, is memory optimizations. Oftentimes, when you optimize your data structure for its memory footprint, you oftentimes find that your memory footprint and your performance, your CPU performance or calculation performance are, if not hand in hand, often very tightly linked at least. For instance, if you're using or having to use an apply statement on a data frame, if you've optimized that data frame to remove redundant columns, it's doing less work. If, let's say, you have a low entropy series of strings and you've replaced those with categorical integer values, you can do much faster operations on that as well. So there's quite a few performance tips in Pandas that you can look into for memory optimization that will also actually yield you a performance optimization in the long run. The final point is there's a couple of third-party tools. So I have spoken about them, but not in any detail. So we can use memory and performance optimization tricks all we want, but at some point you will probably run into size of data or data of an order of magnitude that just kind of exceeds your computer's memory, and you will have to start thinking about using distributed processing frameworks, in which case definitely look into the likes of Spark and Dask. These are worth whole talks and have been dedicated to whole talks in and of themselves, so definitely worth looking into if you're dealing with really big data sets. I spoke very briefly about Cython in the beginning. I will mention it here as a tool because I do believe that if you have a large code base where you have a performance bottleneck in some calculation, some small calculation, it is, in my opinion, a completely valid approach to reformat or rewrite just that one calculation or those few calculations in Cython code. The advantages being that it is much faster than Python code, or let's say pure Python code, and it plugs seamlessly into an existing Python script. So if you do have some really heavy computations, writing some of those methods and functions in Cython is definitely an option you want to consider. The final library that I haven't spoken about here is Number. So Number is one of the just-in-time or JIT compilers. And this addresses a very different part of the Python interpreter structure in order to get performance improvements. And you'll find actually that even if you're using highly optimized NumPy code, Number can still give you huge performance improvements when you're dealing with numerical and mathematical operations. So do bear these in mind and have a look into them. So before I finish this talk, I just want to summarize a few key points. Number one, before you start, decide where you want or actually where you can afford your overhead to be applied. Is this task absolutely performance critical in terms of its timing. Maybe in that case, Python or pandas or NumPy aren't the right tools. You might want to look at a different language or a different framework. On the flip side, if you're dealing with a lot of real world data, a lot of messy data, and it's something where you're going to have to iterate a lot on the code base, then maybe the likes of Python and pandas, because of the speed that they allow you to iterate on your code with, they might be the right tools in that case. But really the fundamental point to take away here is try and think about this and make these decisions as much as you can before you start, because as we've seen, once you have an established code base, it becomes a very, very expensive and costly operation to move that into a new framework or a new language. The second tip, or the second summary point, is very neatly captured by this quote by Donald Knuth. Premature optimization is the root of all evil. Whenever you see these kind of performance tips, it's very easy to think, I'm going to run away now and just do everything that way. But you can't stress this enough. When you're writing code, start off by writing at whatever level you're comfortable with. Make sure it's properly factored, or make sure it's properly sort of packaged and thoroughly tested, and then come back and start worrying about performance improvements. Because if you're jumping into sort of concepts that are still new to you and you're writing code in that way, it's very easy for you to start introducing lots of errors and bugs. So as I said, just make sure your code is working and tested before you start making those performance optimizations. More specifically, when we talk about likes of pandas and NumPy, remember, try and vectorize wherever possible. It will be faster, and as we've seen, it's probably even going to be more legible than using loops and base Python syntax. And I've spoken a lot about vectorization. It's not the be-all, end-all of processing. Sometimes you will have to loop, and there's no shame in that. But if you're going to loop, especially in pandas, make sure you're using an apply statement as opposed to, say, iterrows or a basic loop. But just bear in mind that check you're using apply correctly, because as we've seen, not all applies are created equal. So with that being said, I want to thank you very much for taking the time to listen to our talk today, and thank you very much.